Okay, so as we put these into Matlab, Matlab includes transfer functions in its packages that you guys have access to, right? I think you have to have the signal processing package, the signal processing toolbox to do transfer functions. I believe that's where it comes at. But we have it, so if you downloaded our license and you downloaded all the available packages, you shouldn't have any trouble doing it. So when we look at this transfer function up here, its original one, right? This is in sort of a factored form. But ultimately, this is a rational polynomial, meaning I could multiply everything out and I would have a polynomial in the numerator and I would have a polynomial in the denominator, right? So if I were to do that, it would give me the third form of writing down transfer functions. The top in this case looks the same. The denominator, I would have to FOIL this out. Let's see if I can remember how to FOIL. Right? So the other thing is when we do transfer functions, we typically don't worry about calling it j omega. We call it just s, some complex number, right? So if I do that, I don't have to worry about whether the j's cancel or not. So I'm going to do that right now. So I'm just going to consider this to be s and this to be s, right? So if I do that, I get s squared. Right, first, outsides is 20s, insides is 2s, and they add together, so that's a 12s. And then the last is a 20, right? And we're going to let this be s on the top. Okay? So this now looks like a polynomial. Do you guys remember how to put polynomials into Matlab? Ravina does, because she gets to practice it all the time. Right? So, when we're going to put polynomials into Matlab, Matlab treats a polynomial just by the coefficients of the powers. So we want it in this order, right? And we would look at this and we say, well, this is a s to the 1, and there's a 0 in the s to the 0 position, right? There's no constant term. So I like to define these using the numerator and the denominator. So I just call a variable num, and it's a matrix or a vector with the variables, with the coefficients of each of the powers of s. So in this case, it's a 200. And a 0, right? And then denominator, so den, is the powers of the denominator, sorry, the coefficients of the powers of s in the denominator in decreasing order, right? So the first one, this is s squared, this is s to the 1, this is s to the 0. So I put the coefficients in that order, 1, 12, 20. There we go. So I have numerator, I have denominator, two vectors or matrices. Now I want to create a transfer function. And so here's where Matlab is nice and powerful for you. You just say like t, or in this case actually we called it h, right? So h equals tf for transfer function, just lowercase, and then the arguments are the numerator and the denominator with a comma between them. Hit enter. It's going to launch the package, and then it's going to define the transfer function. There we go. So it has now defined this transfer function, and you get a nice visual look. It matches exactly this form. Matlab always deals with transfer functions in that polynomial form, right? And there are ways you can get that. If you didn't want to multiply these out by hand, you can ask Matlab to do it for you, right? Using like the poly command. Or if you want to factor it back out, you can use the roots command, right? You can do that to get the different values. But once we have the transfer function, the beautiful thing about Matlab is I can just say Bode of h.
Seriously?
Yeah, it's thinking a lot. You really shouldn't have to, except that I just haven't run it yet. And there we go. And notice it is giving you your Bode plot in radians per second. It is the Semilog plot, right? So it has magnitude in decibels over here, and here along the horizontal axis is omega. Powers, here's omega to the negative, 10 to the negative 1, 10 to the 0. So there's your 1. Here's the 10, 100, 1,000, right? And that looks pretty much exactly like what we had. sure I can manage to fit both of those on the screen at the same time for you guys, right? But we start at 0. We're going to go up to something. Here's, if this is 20, this is somewhere in the neighborhood of 30 that it peaks at, right? And then around 10 to, well, certainly down here we see that about 200 is where it crosses 0 again.
Windows left key, Windows right key?
Yeah, I'm afraid it's too small. Right? See, it's just,
Yeah.
well, maybe we can squeeze it in. Here we go. There you go. Close. Yeah, that worked out okay. Oh, yeah, Matlab adjusted itself. That was smart. The book won't adjust itself pretty well. But, so here we see we cross 0 at the point 1, which is just over here, just to the left. And then at 200, we should cross 0 again. Well, where's 200? Well, here's the 100 place. Here's the 200 place. When we come up here, sure enough, that's right at the 0. Right there. And that's 200 radians per second. And we peak at just a little over 20. Okay, it actually stops just shy of 30, so around 25 decibels. Right? There is our exact curve. And we can see now, yeah, it doesn't have these sharp angles in it at all. It's rounded off very nicely around the corners. Similarly, it plots the much more, again, kind of difficult to draw phase plot for us. And there's that very nice, smooth S sort of curve between a 90-degree phase shift and a minus 90-degree phase shift. Okay? Do you have a question on this? That one is way more accurate, of course. Matlab is going to do it much more accurate than we can do it by hand, typically. And so you'll see, right, for all of that, rigmarole we just went through to sketch that by hand, Matlab, boom, done, right? And as it becomes more complicated, Matlab is far, far more trustworthy, right? As long as you type it all in right. But the nice thing, again, is it does show you that transfer function. So you get to see it. And you can double check that you typed everything in right, that all the coefficients are the ones you expected, right? Again, it might get tricky if there's more than 2 or 3 poles, and it's written in this form. If you don't want to multiply it all out by hand, you have to be a little bit careful that you multiply it all together appropriately. So again, just remember your polynomial commands from Matlab and how to use those. If you want to multiply 2 polynomials together, you need to use the convolution command, the CONV command. So that can come in handy as well. So like if I wanted to get this denominator in this form with Matlab, how can let's see if we can show how to do that. So simple things like saying poly, and in poly you can send in a matrix that uses the coefficients that you see. So if I look at just this first term, for example, right? If I say that that's an S plus a 2, S is a 1 coefficient, and 2 is the constant, so I'm going to put them in as a 1 and a 2. I'm sorry, I didn't do that right at all. Sorry. So, the poly command, you enter a matrix that includes the roots. I was jumping the gun there, I was getting to the convolution side. We enter the roots, or in this case, the poles. So in this case, I know if I were to multiply these out, I have one pole at -2, and I have one pole at -10, right? So those are the elements I put in. I'm sorry, I disregard that first thing. So poly will create a polynomial with the roots. So when I have it in this form, and it's all nicely factored, I can usually just do the poly command. And I can verify, in fact, what my denominator ought to be. And I could have just defined that as den, right? I could have said den equals, or whatever I wanted to call it. I'll call it den 2 in this case. There we go. And now, I can do a transfer function. And there it is. And sure enough, it's exactly the same as the one we had before. So that just double checks my foiling. Question, Brian?
No.
So then the other commands that can come in handy, again, might be like convolution. So if this is like, this is a simple first order pole, it could be squared or it could be cubed. There could be some power there. In which case you want to figure out what that is in polynomial form. So if I had something like that, I might use convolution. That we can do you can actually raise the vector to the power. Right, Ravina?
Mhm.
You can raise the vector to the power, like the
Yes,
polynomial to the
yeah.
power. It'll do that one for you. You have to do just the caret, right? No dot caret, just caret. But if they were two different ones, so another way of approaching this is I could say, let's just call it P1, and the P1 is just going to be the first term seen as a polynomial, so 1, 2. And then the second polynomial, the second whole term, the second polynomial will be 1, 10. Right? And if I want to multiply those two polynomials together, I can use the convolution. So I can say con of P1 comma P2, and then it multiplies those two polynomials together. And in fact, in this case, it gives me exactly what I expected. Right? That's what they come back out. That, again, can be handy more if like there's a term down here that's a quadratic, so it's not factored nicely. You don't know what the poles and zeros are immediately. You might just rather do the convolution term. And so, again, but once I know these, that is the term that I want to define as the denominator of my transfer function.
That's just coefficients though.
It is just the coefficients. And so how do I know what it really is? You just start at the right. That's the s to the 0, right? So the constant term. S to the 1, S to the 2. If there were more, it'd be S to the 3, 4, 5. And so it lays it out very nicely. Always in descending order. Okay? So that can be very handy. Again, those are just good polynomial commands to remember. If you haven't used them in a while in Matlab, good to kind of brush up on those. And then that the transfer function and the Bode commands are, I find those to be extremely useful and powerful. It is possible to do a Bode plot in multisim, but it's oftentimes not as handy for classwork, for homework, because it takes the circuit you draw and spits out a Bode plot, right? So it does a simulation. It varies the frequency and it plots the points, a lot like you would do if you were trying to do that measurement in the lab. But if you're doing the homework and they just say, here's a transfer function, show me the Bode plot, that's going to be a lot harder for you to put into a circuit form in multisim, and you want to be able to just drop that into MATLAB. So if you already have the mathematical expression for the transfer function, MATLAB is your best friend. Right? If you only have a circuit drawn, you've got an option, either just putting it into multisim and letting multisim do the simulation and tell you what its behavior looks like, or you can look at the circuit, write down the transfer function by using your standard KVL or KCL, whatever method you want, to find the output divided by the input, right? And then use that algebraic transfer function and drop it into MATLAB. So you've got a couple of options of how to approach it. And again, with a little bit of experience, you guys will start to find that you'll recognize a lot of the transfer function, a lot of elements of the circuits that result in particular behaviors in the transfer function. So one of those that's related to this band pass filter